Sir, good morning, sir.
So good morning, all of you.
Good morning, sir.
Yeah, already somebody has co-host. So please, very careful about if anybody joining, please allow them. I think Joshna is the co-host. Okay. So today, I'm going to start frequency response of amplifiers. Okay, the contents of this module: Miller effect and poles and zero concept, common source stays, source follower, and common gate amplifiers, frequency response, and later cascade stage and differential pair. All we studied. So stages, common source stage, and common gate, source follower, cascade, and differential pairs. We already studied. This we studied there as an amplifier. What is the input impedance? What is the output impedance? What is the gain? These parameters we have calculated. In this module especially, we are going to calculate frequency response. How the gain is frequency response means simply you can understand one thing, how the gain of the circuit or gain of the amplifier varies with respect to the frequency. That is the thing we need to discuss here. Okay, so some basics we need to discuss here. The analysis of simple amplifiers has thus far focused on low frequency characteristics, neglecting the effect of device and load capacities. This is the first thing: low frequency and high frequency and mid range of frequencies. How the characteristics of an amplifier will vary. So in this course, we need to neglect or assume some of the parameters or some of the effects or ideal case. Ideal case means there is no effect with them. Okay. So in most of analog circuits, the speed of the circuit is states with many other parameters. The speed of the device or circuit. I'm talking about only circuit, of course. So depends on many parameters. What are the parameters which influence the speed of the circuit? The first thing is gain, power dissipation, and noise. These three are not only these three, many parameters are there, but most of the time, so these three parameters will influence the speed. If the gain is the circuit is main parameter, and power dissipation, how much power the circuit is going to dissipating, and the noise carrying capacity of the circuit. So these three parameters, the speed is always trades with these three parameters. So it is therefore necessary to understand the frequency response limitations of each circuit. Yeah. So while you are explaining or analyzing the frequency response of a particular circuit, what are the limitations? Okay, limitations means at how much frequency your circuit do the better performance. That is called the limitation. Here we'll study the behavior of single stage. Single stage means common source, source follower, common gate stages, and differential amplifiers in the frequency domain. We have two different domains we need to analyze circuit. One is the time domain analysis, one more is the frequency domain analysis. So in this module we will discuss the frequency domain analysis. Frequency domain analysis means what? The response of the circuit, particular circuit, with respect to the frequency, how it's showing the characteristics variations. So following a review of basic concepts, so and analyzing the high frequency response of common source, common gate, and source follower stages. So finally, so there are two other things are there as we have in the syllabus, cascode and differential amplifiers. So for them also we need to discuss what is their frequency response. Some general conditions we need to discuss before entering into the actual subject. The first thing is mass device exhibits 4 types of capacitances. Okay, one is the gate to source capacitance, one more is the gate to drain capacitance, one more is the drain to body capacitance, one more is the source to body capacitance. There are 4 capacitances. If you expand all the 4 terminals between each 2 terminals, each pair of terminal, you can find one capacitor. Okay, gate to source, and gate to drain, 2 things. And so drain to body and source to body. There are 4 capacitors. So that means knowingly or unknowingly, so the capacitor will show will form these 4 capacitors. Hence, the transfer function of the CMOS circuits become complicated. So because of existing of these transistors, so generally, suppose if you take a MOSFET, so this is our MOSFET, for example. This is our MOSFET. This is the body. This is the gate, source, and drain. So this is one capacitor. This is one more capacitor. This is one more capacitor, and this is one more capacitor. So like this, you have a 4 capacitors. 4 capacitors. So because of this is the gate to source, CGS. This is the gate to drain, CGD. And this is the body to drain, so CDB. This is the C what? So SB. So because of existence of these capacitors, the equivalent circuit of this MOSFET is difficult to draw. Okay, and it's complicated whenever the device is having so this many capacitors. Okay, so the equivalent circuit is difficult to draw. Okay, so the transformation of CMOS circuit becomes complicated, calling the approximations that simplify the circuit. Yeah, so to analyze this complicated circuit, we need to simplify it. So by approximating something, by discharging something, you can get the simple circuit. Then you can do the analysis. Okay. So MOS device exhibits 4 types of capacitors as shown in the picture. Just as drawn. The transfer function of the CMOS circuit becomes complicated. Okay. So because of why the complication comes? Because of these 4 capacitors. So how to simplify it? By considering some approximations. What approximation we must be considered to simplify the circuit, that we will discuss. Got my point? Hello?
Yes, sir.
Yeah. Yes. So here we introduce the 2 such approximations. One is the Miller theorem. This is one of the approximation. And one more is the poles and zero concepts. Poles with the nodes. So these are the 2 approximations we must be considered for the simplify the circuit. Why the circuit is complicated? Because of the capacitors. But for the analysis, we must be simplify it. So by taking the two approximations, one is the Miller's theorem. I think the Miller's theorem is very familiar word with you for you. So because from the user onwards, we are using the Miller's theorems. So for example, if you take any two-terminal impedance, okay. So Z is the two-terminal impedance Z. So you want to split this Z to the input and output side, then so we can say Z is equal to V by I, and V is the voltage and I is the currents, you know that. So for example, Z is the impedance. Any two terminal impedance means it may be a resistor or a capacitor or maybe a inductor or maybe a combination of any of these devices. So that is called the two terminal impedance. Suppose Z is equal to 1 by Cs for a capacitor. Z value is 1 by Cs for capacitor and Z is equal to Ls for the inductor. Z is equal to R for the resistor. Okay, so the transfer function of circuit, what is the purpose of the transfer function? If you know the transfer function of circuit, suppose this is a circuit or a system. If you know the transfer function of this fellow, then you can find the response, frequency response of this fellow, this entire circuit. Okay, by applying the some input value. The input may be a what? Suppose this is the input and this is the output. Input may be a cos omega t. Okay, so by applying this input signal, this is the sinusoidal signal. So where omega is the frequency, okay, varying the frequency value from 0 to infinite, you can observe the response at the output. How the circuit is behaving for the input signal a cos omega t, where the frequency omega what varying from 0 to infinite. So at the output, how what type of response you are getting, that is called the frequency response. So the first and foremost thing to do the frequency analysis or frequency response, to draw the frequency response or do the frequency analysis, what is the requirement? Transfer function of the system or circuit is required. So once you know the transfer function, the output you can observe, the analysis output response you can be observed by applying some input. What type of input is applied? Sinusoidal input is applied in the frequency response. Okay, so sinusoidal input signal whose value may be a cos omega t, where omega is there. So you can vary the omega value from 0 to infinite and you can observe the output, what type of response the circuit is producing. So that is the what? The frequency response definition. Got my point?
Yes, sir.
Yes. Yeah. So this is the frequency response. Suppose h of j omega is the here h of j omega. Generally, suppose as I draw the picture. So this is my picture. This is my input, and this is my output. If this is the system of circuit whose transfer function is, you can say h of s. So to find the frequency response, s must be replaced with the j omega. So then this system transfer function becomes h of j omega. That's it. Yeah. So at last, on the last line, you have h of j omega is equal to rc j omega plus 1 inverse. That means 1 by, simply you can say 1 by 1 plus s. In place of s, you should write s into rc. Sorry, s into rc. This is the low pass filter. Low pass filter. Okay, low pass filter transfer function is 1 by 1 plus src. For high pass filter, it is a 1 by, so 1 plus 1 by src for high pass filter. Similarly, band pass filter. We have three different types of, not only three, so we have many, but we need to discuss three ranges. One is the low frequency response, one is the high frequency response, and another one is band pass response, means between the high and low frequencies. So low frequency transfer function, a low pass filter transfer function, high pass filter transfer function, and band pass filter transfer function, you must be known. So this is the low pass filter transfer function. H of S is equal to 1 by 1 plus SRC. In place of S, you can substitute j omega. Then it becomes the 1 by 1 plus RC j omega. So once you know the transfer function of the circuit or a circuit or the system, then you can find two things. One is the magnitude, one more is the phase responses. Magnitude response and phase response. Okay, so that is the story of what we are going to doing here. We will do here. Sorry. So once again, I am going to tell you mass device. If you consider the mass device, as it's having the four terminals, so it can exhibit the four different types of capacitors. So whenever the capacitor is associated with all this, whenever the MOSFET is associated with all these capacitors, equivalent circuit or analysis, it is very difficult. So that we must be simplify this complicated circuit by using some approximations. One is the most popularly we are using is Miller's theorem. And what is the concept of Miller theorem is, suppose if you take any two terminal device whose impedance is Z, okay, so and flowing the current of, so current is I and voltage is V across the Z, then so we must be this Z two terminal device Z can be replaced with the Miller's theorem. What he's saying here is, for example, Z is any two terminal impedance means it may be resistor, inductor, capacitor. If it is inductor, Ls, Z value. If it is capacitor, 1 by Cs is impedance value. If it is a resistor, simply Z is equal to R. So to find the frequency response, what is the requirement? The requirement is transfer function. Okay. So once you know the transfer function of the system, the output of the system or response of the system can be easily analyzed by applying a sinusoidal signal. So A is cos omega t, omega t at the input, and where omega value should vary from 0 to infinite. Okay. Likewise, what is the, so different circuits will have a different transfer functions. For example, H of S is the transfer function of a system or a circuit. So we have a different circuits means for the frequency response point of view, you can say three range of frequencies: low pass response, low frequency response, high frequency response, and mid range of frequency response. So for low frequency response, low pass filter is required. For high frequency response, high pass filter is required. For mid range of frequencies, so we need the band pass filter. So each filter you can differentiate with its respect to transfer function. For example, if you consider the low pass filter for low frequency response getting, so whose transfer function is H of S is equal to 1 by 1 plus R S into RC. As I depicted earlier, what happened? So if you want to know the frequency response, then so wherever the S is there, you must be replace it with the j omega. So once what is the j omega? In the j omega, you have a omega value. So omega is the frequency component. Okay. Yeah. So the primary interested in the magnitude of T. So TF transfer function. If you take the transfer function, so by applying the input, you can find the output. From the output, you can find two things. One is the magnitude, one more is the phase. Magnitude response and phase response. So, okay. So magnitude response, see, it is a low frequency response or low pass filter response. Low pass filter response or low frequency response. This is the Bode plot. Low frequency. So this is the 0, y-axis is the gain, and x-axis is the omega. Omega is varying from 0 to infinite. So I think, see here, for lower range of frequencies, you have a full gain. So once your frequency is crossing the lower cutoff frequency or critical frequency, then the gain is decaying. So, or you can say one thing, as free omega value is small, you will get the full gain. Okay, constant gain. So once the omega value crossing the corner frequency, then it is decaying. So it means this particularly this response is belong to the low frequency response. Okay, low frequency response. Even if computed exactly, some transfer function do not offer must insight. Therefore, study numerous special cases by considering the extreme conditions. If the load capacity is very small or very large like that. So what is saying? As we discussed, of course, the transfer function of the circuit or the the system is very important for understanding the or knowing the frequency response of the particular system. Okay, so even sometimes what happened, whatever the transfer function we have, transfer functions we have for a particular circuit, I think will not do always better response. Will not give always better response. Why means there are many conditions which influence the response. Okay, so that special cases we must be considered. So like what is that one? Load impedance may be sometimes small, sometimes large. Okay, sometimes small and sometimes large. These are the approximations. So without suppose if you are not knowing, not approximating them, then the response of the filter of the circuit, I think not as shown in the pictures. Yeah, this is the band pass filter response. Band pass filter response. This is the low pass filter response. Low pass filter. See, band pass filter means, say this is the lower cutoff frequency, this is the upper cutoff frequency, higher cutoff frequency. The response between these two frequencies only the constant. So rest of the frequencies, the response is not constant. And here is the only below the low frequency, lower cutoff frequency, your gain is good. So above this frequency, it falls down. Yeah, this is the high frequency response or high pass filter. High pass filter response. So high pass filter means it allows only high frequencies, reject all other frequencies. So band pass filter means it allows a band of frequencies and reject others. So low pass filter means it allows only low frequency signals and reject all other frequencies. See, here is the upper cutoff frequency FH. So below this FH, your gain is not constant. But after FH, your gain is constant. These are the three different types of filters. Understand? Hello?
Yes, sir.
Yeah. So the requirement is this type of responses to find. To find this type of response. This is the magnitude response. All three are the magnitude response of each individual one. Okay. So all these responses, to get all these responses, the requirement is transfer function of the system. Yes, magnitude. For example, you have a one component z is equal to a plus jb. So magnitude is nothing but mod z is equal to a square plus b square under root. Means this is the real part, this is the imaginary part. Real part square plus imaginary part square under root. Okay. So this is the magnitude. Similarly, you can find the angle also. That is the tan inverse imaginary by real. What is the imaginary component here? B. By real component is A. Yeah, this is the magnitude. This is the magnitude. This is the phase. You can take this two for sketching the respective analysis or response. Okay. So zeros and poles. What is the zeros and what is the poles? So this is my transfer function h of s. Generally, transfer function is nothing but output v naught of s by input v in of s is equal to it has some numerator and some denominator. Some numerator and some denominator, NR and a DR. So the roots of the NR are called the zeros and roots of the DR are called the poles. Roots of numerator and roots of denominator of the transfer function called what? So zeros and poles. Yeah. So now, according to the Bode's approximations, of course, Bode plot is the one of the frequency, one of the good, best frequency response plot. Okay. So according to Bode's approximation, the slope of the magnitude of the transfer function increased or decreased by 20 dB per decade. Okay. And when it is increased, when it is decreased. So this is my numerator. And this is my denominator. Numerator are called the zeros, roots, and denominator roots are called the poles. Until up to this one, you know perfect. So now, if you want to draw the frequency response of this fellow on the Bode plot, okay, when one pole comes, the function is the transfer function increased by 20, and one zero comes, it is decreased by 20. Okay, plus or minus. Suppose, for example, this is my Bode plot. This is the omega value. This is the gain. Suppose you are here. One frequency at this frequency x. Okay. Then if you have 1 0, then so this is increased by 20 dB per decade gain. Suppose there is a one pole comes here, one pole, then it is decreased by 20 dB per decade. So like this, the gain in the magnitude response plot either increased or decreased by 20 dB per decade. So in with the respective pole and zero concept. Okay, I hope you understand the pole. What is the pole? What is the zero? And so how the what the 20 dB the gain 20 dB changes per decade. Each decay means 10 points or 10 divisions, okay, per each decade. So 20 dB gain changes for the pole or zero, either upper that means increasing or decreasing based on the root, either pole or zero. Hello, okay.
Okay, sir.
Yeah. So now comes to the Miller's effect. What is the Miller effect? So Miller effect is nothing but simply Miller theorem says, Miller theorem decomposition of a floating impedance Z into two grounded impedances. For example, yeah, here is circuit. Yeah, this is the, if you take this one, this is the floating impedance Z. Means floating impedance means I think this impedance is having is existing between the nodes X and Y. Nodes X and Y. There is no ground, of course. So I want to split this Z into two components. Okay, so two grounded components. So means simply I can say I need to do like this. Yeah, this is like this. Yeah, this is the one component. This is one more component. So now ground is there. See, the floating impedance Z is split into two parts, decomposed into two parts, two impedances, grounded impedance. Simply, there is no ground here, but here is a ground. Each impedance is having. So Z is, I want to replace this like this. That is called the Miller theorem. Miller's theorem. The decomposition of floating impedance Z into two grounded impedances, proven that useful in okay. So now see, what is the Z1 value, what is Z2 value you want to find. So Z1 value is nothing but, see, Z by 1 minus AV. AV means what? Gain. That is equal to, so Z by 1 minus, okay, so AV means Vy by Vx. Similarly, Z2 is equal to, what is that one? Z by 1 minus AV inverse, that is equal to Z by 1 minus 1 by AV. 1 by AV is what? AV is Vy by Vx. So that is equal to Z by 1 minus, so Vx by Vy. That's it. So this is the floating impedance that we want to divide like this, grounded impedances. Okay, so you use Z1, Z2 values, you can calculate like this. Z1 is equal to Z by 1 minus AV, and Z2 is equal to, so Z by 1 minus gain inverse. So proof, the current flowing through Z from X to Y is equal to, what is the current flowing in this one? So this direction or this direction, you can find two directions are same. Suppose only current is flowing in one direction, this is not valid for the Miller theorem. Okay, so since the current is flowing either from X to Y or X to Y to X, okay, the voltage at this node is, you can say Vx, and no voltage at this node is say Vy, then the current I is equal to, so Vx, this one, minus here voltage is Vy by impedance Z. Okay, so for the two circuits to be equivalent, the same current must flow through Z1. Thus, see, Vx minus Vy by Z is equal to, you can write Vx by Z1. Vx by Z1, this one. This is whatever the current is flowing in this one is equal to, so Vx by Z1. Similarly, here also, from this equation, you can find the Z1 value. How much you got? Z1 is equal to Z by 1 minus Vy by Vx. You can say this is the Z by 1 minus, this is the gain AV gain. Okay, so the next one is Z2 value. So in Z2 value, this is equal to, in place of this, you can write Vy by Z2. So Vy by Z2. So after, so you can find the Z2 value here, then you can get the Z by 1 minus, so Vx by Vy. What is the Vy by Vx? AV. What is the Vx by Vy? AV inverse. That's it. AV inverse. So remember, so whenever the Miller's theorem is applicable, where the floating impedance Z can be decomposed into the two grounded impedances Z1 and Z2. So Z1 value is always, Z is divided with the 1 minus AV, and Z2 is equal to, Z is always divided with the 1 minus AV inverse. Okay, got this Miller theorem? Are you okay? Any doubt?
No, sir.
Yes. So Miller theorem does not stipulate the conditions under which the conversion is valid. Yeah, sometimes the Miller theorem is not applicable, as I told you. Okay, so in the previous the pictures, since the current is valid in both the directions, the Miller's theorem is applicable. Suppose current is valid in one single direction, it is difficult to apply. Miller's theorem proves a useful in cases where the impedance Z appears in parallel with the main signal. Yeah, here is, if you take this one, so this is the main signal, one path, this is another path. So now this is the parallel, Z is parallel to this one. So Miller's theorem you can apply, so whenever the impedance Z is parallel with the main signal. Okay. So equivalent circuit reveals that Vy, suppose if you take this equivalent circuit. So for example, this is one circuit, let us assume. Here Vy means here is not equal to minus AVX. Vy means here voltage is not equal to this one at high frequencies. Hence CF cannot be simply multiplied by 1 plus A to yield the input capacitance. So CF, if you take the CF, this is existing between this side and this side. So this is the floating impedance Z. This is the floating impedance Z. I can replace this CF, this Z. I can split this and I can connect like this. I can connect like this. So this is, you can remove this one. Okay. So then what is the value of this one and Z2? We want to calculate, we should calculate as per previous analysis. Okay. Here my suspect is Vy is not equal to minus AVX at high frequency I'm talking about. CF cannot be simply multiplied by 1 plus A to yield the input capacitance. Input capacitance is Z1. Output, because of this is the Z, this is the capacitor value. When we are going to decompose and keep like this side and this side, so this becomes the input capacitance, this becomes the output capacitance. So usually the input capacitance or input impedance Z1 is the what? So impedance is multiplied with the 1 plus AV. But in this case, it is not correct. It is not true. However, in many cases, we use the low frequency value Vy by Vx to gain insight into the behavioral circuit. Okay. So I want to show one more. Yes. Slides there. Is it okay? Visible?
Yes, sir.
Yeah. So here I want to go for simple examples. Yeah, here is one example. So in 6.1. So what is saying? Consider the circuit shown in figure where the voltage amplifier has a negative gain. Voltage amplifier has a negative gain whose value is minus A and is otherwise ideal. Okay. What is saying? Calculate the input impedance of the circuit. He's asking. Just for the circuit, we want to find the input impedance. Okay, we'll see. Yeah, this is. See, this is the circuit. This CF is an impedance which is parallel to the main signal. Okay, so now in the B, picture B or figure B, this A, this CF is the existing like this. So it should be replaced with like this Z1 and Z2. Z1 and Z2. You know the values. What is the Z1? So Z is equal to what here? Z is equal to 1 by what? So S into CF. So now here Z1 is equal to what is the formula? Z by 1 minus AV or A, you can say. Whatever you can say. Or he said the A gain is A, so that you can write the A. A is the open loop gain. So that is equal to, this is the Z1, that is equal to, what is the Z? Z is 1 by S into CF by 1 minus AV. 1 minus A otherwise. This is. That means this is equal to 1 by 1 minus or 1 minus 1 is plus because of it is a minus. So it becomes plus, okay. Plus A into CFS or S into CF. This is Z1 value. And Z2 value is here. What is that one formula? Z by 1 minus 1 by AV. A otherwise. So this becomes plus, of course. Z is 1 by CFS by 1 plus 1 by A. So then take the common and everything, then it becomes what? So 1 by CFS is multiplied with A into 1 plus A. That's it. Or A by something. Okay, A by, so this A is not there. So A by 1 plus A into CFS. Okay. This is the input impedance is equal to how much? This is the input impedance is Z1 plus A into CFS, because 1 by Z is okay. So we call this as a Miller multiplication. This is called the Miller multiplication of the capacitor. Miller multiplication of the capacitor. Okay. So why is CF is multiplied 1 plus A? Got these points? Hello, understand these equations? Hello?
Yes, sir.
Okay. Yeah. See, using Miller's theorem to convert the circuit to that shown in picture B, we have Z is equal to 1 by CFS, okay, and Z1 is equal to this one. That is the input capacitance is equal to CF is multiplied by 1 plus A. That is. So here CF is this feedback capacitor is multiplied with 1 plus A gain. So we call this effect as the Miller multiplication of the capacitor. Okay. So why this CF is called here? Why the CF is multiplied with 1 minute? So why the CF is multiplied with CF is multiplied with 1 plus A. So in the Miller multiplication. So because if you consider this picture, the last picture. So I am going to apply a change in step. Value is delta V. Okay. So apply a voltage step at the input and calculate the charge supplied by the voltage source. So because of this step voltage, how much charge is supplied from here to Y? Okay. A step equal to, so at this X is equal to, so X is equal to delta V is applied. At X you are applying the delta V. At Y the corresponding change is same delta V is multiplied with the gain. What is the gain? Minus A. This is the change at Y. Change at X. This is at X, this is at Y. So at the node X means at this point, if the change in voltage is delta V, then the corresponding change at Y is minus A delta V. Okay. So which yields the total change of, what is the total change? Means X minus Y. Total change is total change is equal to Y minus X. What is the Y? So Y is this much. So that is delta V minus plus. So A into delta V. This is the change. You can take the delta V common, then 1 plus A into delta V. So this is the change which appears across the capacitor CF. So you can say one thing. Since the change across the voltage across the, okay, CF is 1 plus A into delta V. The capacitor, the charge drawn by the capacitor from V in is equal to how much? So 1 plus charge Q is equal to CV formula. Q is equal to CV formula. What is the C? C is the CF. Is multiplied with the voltage change is this much. 1 plus, so delta V into 1 plus A, 1 plus A into delta V. And this is the charge drawn from the CF. So from this you can understand CF is equal to 1 plus A into delta V. Okay, this is the charge. So then you can say the equivalent input capacitance is this much. This is the equivalent input capacitance. So is multiplied with the delta V. The change in voltage across at the input will be appear as the output. Okay, this one. Hello.
Okay, sir.
ఏంటంటే రామకృష్ణ గారు మాట్లాడట్లేదు.
ఉన్నా సార్.
That's the second one. And third, another problem is a student need a large capacitor for filter and decided to utilize the Miller multiplication. What is the Miller multiplication in the previous case? So input capacitance value CF is multiplied with 1 plus AV. That is the Miller multiplication. Explain this issue. So first consider this picture A. So this picture, in this picture, you know about this fellow. Just now you have discussed. So then what is the input impedance here? Input capacitance here. CF is multiplied with 1 by 1 plus A. Okay. So now the issue related to the amplifier, particularly to its output swing as exemplified by the implementation in the picture B. This is the B. Okay. If the voltage at X swings by V0, yeah, this is the voltage swing V0. This is the voltage swing V0 at the X node. If the voltage X at X swings by V0, which one? Your input is Vin. So this Vin will be swings at the X node X by V0. Then Y must be accommodate a swing. Since the input of this amplifier is having swing, output must be also produce swing. So this is this circuit. Okay. So what is the swing at this point? Output, because input swing is V0 and gain of the amplifier is A, then output swing is, so gain is multiplied with the input swing. So A into V0 without saturating the amplifier. So in addition, the DC level in Vin must be compatible with the input amplifier. Okay. So this is the another example. Yeah, this is another example. He's asking to calculate the input impedance of the circuit. This is the what? Oh, this is what? Can you recollect? Remember this one? Are you okay? Can you test your memory? This is the CG amplifier. CG stage, common gate. So this is the X, this is the Y, and this is the mass device, and there is a R0. If you treat this as a Z, since it is the floating impedance, you can split this impedance into two parts. One is this side, one more is this side. This side is say Z1 and this side is say Z2. Z1 value is Z by 1 minus A. So Z is how much here? R0. R0 by 1 minus AV. And here is the Z2 is the R0 by 1 minus 1 by AV. Are you understanding conversion of this one? Splitting this R0 into two parts. Is it okay? Hello?
Okay, sir.
Okay. So now the input impedance is, so the gain of the circuit, gain of the circuit, already we calculated in the third module. So gain is AV, you can say AV of this circuit is, so 1 plus GM plus GMB into R0. This is the gain. Okay. So the input resistance is given by the parallel combination of, yeah, what is the input impedance of this circuit? So after splitting this R0 into these parts, then what is the impedance? Rn. So Rn is parallel combination of this one and 1 by Gm. So this is equal to input impedance is Rn is equal to, what is that one? Yeah, so Z1, this Z1 is parallel combination with the 1 by Gm plus GMB. So that is called, what is Z1? Z1 component is R0 by 1 minus AV is parallel combination with 1 by, so Gm plus GMB. That's it. Okay. So while you are calculating GMB value, that means parallel combination of this fellow, AV is what? AV value already here is there. AV value. substitute this value. But in this value, in the gain value, 1 plus gm into gmb plus r naught. So this one is very small compared to this term. You can neglect this one and take this one. Then what happened? This r naught and this r naught cancels. Then finally, yeah, this is. Yeah, here is a Rn value, as I told you, this one. So since this one is small, neglect this. Later this one is small, neglect this. Then minus R naught by GMB, GM plus GMB into R naught remains this side. Is parallel with 1 by 1 by GM plus GMB. This R naught cancels. Then this is the one value. So of course, this is the infinite. This is the infinite. So it is having the input impedance is infinite value. Okay. Hello.
Okay, sir.
Yeah, I will stop here for today because next class you have. So I will stop here. So please stay for some time because I want to take the attendance. Yeah, 1 minute. It's updated. Yeah, Tarun presented. Sushma
Yes,
presented.
sir.
Yeah, Vidya. So anybody can help me. Vidya presented or not?
No, sir.
Yeah. Ashik presented. Yeah, Chandu presented. Suresh presented.
Sir.
Pratisha presented. Yeah, Pratisha presented. Iyengar presented. Joshna presented. Pavani presented. Mahendra?
Presented.
Mahendra.
Present,
Yeah.
sir.
Yeah, okay.
Present, sir.
Okay. Only one absent.
Yes, sir.
Okay. Swavat. Thank you. So any doubts, please?
Hello, sir.
Any doubts, please? Any doubts?
10 absent ఉంది సార్ నాకు.
ఎప్పుడు?
10 సార్, డేట్ 10th.
Yeah. I will rectify it, no problem. Okay.
ఓకే సార్.
Yeah, I will stop this meeting. Okay.